Hi, welcome to How Ion Pumps Work by Gamma Vacuum. If you're new to ion pumps, you'll find this very useful. If you've used ion pumps in the past and know how they work, consider this a real nice refresher. Basically, this is what they look like on the outside, which is essentially a stainless steel chamber. However, on the inside, what you'll find is a lot of additional components that you certainly can't see. We start with a feed through and an anode assembly made out of stainless steel anode tubes. Those are isolated from the rest of the system, electrically isolated that is. Pointing to the green there is cathodes that are at ground potential along with the rest of the system. And external to those are magnets and pull pieces, sometimes called flux plates, that are on the outside of the vacuum chamber. Looking at this in a side view, we're going to go ahead and start with that grounded vacuum chamber. So this would be your stainless steel wall isolating atmosphere from the vacuum inside. On the outside of that chamber, we're going to add very strong ferrite magnets. Now those magnets are going to create a high magnetic field, and so to concentrate that field just where we want it, which is between the magnets, we put a magnetic steel pull piece or flux plates around that to capture that. And again, on the inside there's our grounded cathode plates. And internal to that, we are actually going to start drawing our electrically isolated anode rings. If we go ahead and take a close look at this, you'll see that in this configuration, that strong magnetic field between those two magnets at about 0.12 Tesla goes through the anodes, cathodes, and the vacuum chamber walls. There it is. Zooming up on that, we're going to actually rough this pump down to 10 to the minus 4 torr or lower if we can, and go ahead and turn it on. 7,000 volts is what we typically use, but the ion pump will operate anywhere between 3 and 7,000. Free electrons are going to get pulled towards that anode assembly, but they're going to get caught in that magnetic field and rotate around it. This is actually called magnetron motion, and the electrons get trapped until they actually hit something like a gas molecule. And because there are so many electrons moving around in that electron cloud, they're bound to hit a gas molecule eventually. In our example, let's go ahead and use oxygen. Here's our oxygen molecule in green, our electron. Those two are actually in motion and they're going to collide. When they collide, they're going to create a positively charged ion. And we're going to go ahead and draw that ion here in red. And remember, that's in a positively charged anode tube. It's kind of like putting two magnets together. Two north poles don't want to go together. And what's actually going to happen is that positively charged ion is going to move towards the grounded cathode plate at a very high velocity. And when it hits that plate, it's going to sputter, and there's going to be two things that happens. One is a chemical reaction. We use titanium as our material, and that's oxygen is going to chemically combine with that titanium. And at the same time, there's going to be a physical reaction, and that impact is going to spray or sputter titanium molecules all over. And over time, enough molecules are going to sputter onto that titanium that you will actually have a buildup of those titanium compounds and titanium directly all over the walls of those anode tubes. And over the years, that cathode will eventually have craters formed from all the impacting ions. I hope you've enjoyed this presentation, and feel free to contact us at gammavacuum.com with any additional questions.